Thank you, Julie and Mandy. Before we jump into Shreya's lecture, are there any questions about the homework or about, I think I got an email, somebody asked to go over one of the homework questions.
Was it question 6?
It could have been. Let's go over question
That
6.
makes me think fire.
It was the one about the pennies.
Yeah, can you please go over that?
That makes me think you're like.
I took a screenshot of it, it made me so mad. I was thinking.
Oh.
In the morning when the funding was like, I think I figured it out, and then I was like, wait, it's not.
I was like, okay.
Dang.
So we'll go over the penny question and then we'll go over any other questions too afterwards. I'll use this marker for it. If you were to flip a coin once, you'll get heads or tails, right? That's the first time. The second time you flip it, you'll have either heads, tails, heads, or tails, correct?
Yeah.
So if you flip it one more time, these are all the options that you might have. You could have heads. You could have heads, tails. Heads, tails, heads.
Or heads, tails. Good job.
Thank you.
Patterns are her thing.
Tail, heads. Tails, heads, tails.
You lost me at heads.
Tails.
Good job.
I got the last one down.
Does that make sense how we went from here to here?
Yes.
If not, we'll talk about it a little bit more. You got that, Josh? Okay,
I don't,
you flip it one time, you'll have either heads or tails.
yeah.
The second time you flip it, all the possibilities are, the first one would have been heads, the next one heads, or it could be heads and tails. Or you could have gotten tails and heads, or tails and tails.
Okay.
Does that make sense?
Yeah.
So you flip it a third time. If you had gotten heads the first two times, the next time could be either heads or tails, right?
Yeah.
And if you had gotten heads the first time and tails the second time, you could have gotten either heads or tails for the third time.
Okay.
So branching this out like this allows us to see every single possible outcome that could have been. So there are 8 possible outcomes. All heads, and then let's start counting these together. So if you have 0 heads, how many of these have 0 heads?
One of them,
Just one. And how many of these are there total?
8.
8. So 0 heads is 1 out of 8. How many of these have 1 head?
2, 3, 4,
3.
3.
Okay.
How many of these have 2 heads?
One,
2,
3, 4,
3.
3.
3.
And how many of these have 3 heads?
1. I saw the thing and I thought that it was like 1/8, and then I was like, oh, but since that one says 2, then 2 has to be like 1/4, and then 1 has to be like 1/2. For some reason, that's what my brain did. I got them wrong, and I was like, I'm so confused. I tried like 50 different things, and I was like, none of this is working. I'm angry.
I feel that.
I'm hungry.
That's what I did.
Sleep deprived. I just ended up putting a random answer, and I was like, we'll figure it out tomorrow.
I think that's so weird because honestly, the only options we have is heads and tails. So like, is there really a better possibility that you're gonna get three heads in a row, or is there a better possibility to get 2 heads than 3 on paper? Like,
Yeah, you're more likely to get 2 heads 2 out of 3 heads than 1 head out of 3, because you have all these, you have 3 options to get that as opposed to just 1.
That's weird. Okay.
And if you were to do this iteration 1,000,000 times, then you would have a very low error term, and it'd be a lot closer to these numbers.
Alright.
And we'll talk about the error term a lot. Actually, that's what most of this lecture today will focus on. Anybody else have any questions about this? Okay. Any more questions about the homework?
The 95% interval compatibility thing.
Yeah,
Go over that,
confidence
please.
interval. Yeah. We'll talk about that a lot during today, but let's,
Oh, okay.
you want to talk about one
That's
homework questions
weird.
first?
Yeah, I think
It's number,
Talk about the same.
is it number 9?
I think it's number 9, because it says no one focused 50 times, and then at the end it's like the 95% confidence interval is not contained 50%.
That one,
Number 9?
I think so.
Because I kept getting confused every time one of the questions was like, create a confidence interval, so the chance of picking whatever, and then it's like number to number, like blank to blank, I did not know how to do that, could not figure it out.
Why did we do that?
Number 9 is the Public Religion Research Institute conducted a survey of 1,033 adults. That one?
I'm looking.
Yeah.
I think, I don't know. It's not letting me pull it up.
How about if we go over the homework or the lecture, and then if that clears things up, then great. If not, we can talk about it more.
Yeah, for sure.
That work?
It's crazy. I bet. I was confused.
Why she started talking. Your mic's here. Incorrect.
There's one example that's not confidence intervals. It's this first one, and then we'll go into confidence intervals. If you were to roll a die twice and you wanted to get even numbers both times, how do you compute that? There's 2 ways to do that. One is half the numbers on a single die are even numbers. So if you were to roll the die on a balanced die, you would there's a 50% chance that you have an even number. The second die that you toss is also a 50% chance that you can multiply those together. 50% times 50% is 25%. The other way, so similar to how we set up this branch, you could do something like that. I wrote out all the combinations of dice. If you were to roll 2, you might get 2 1s, you could get a 1 and a 2, 1 and 3, and so on. The even numbers, if you were to count out what the even numbers were, and I put those in red, we count out 9 of them. Out of 36, you have a sample space, so 9 divided by 36 is 25%. And so you have a 25% probability of rolling a die twice and getting, or a pair of dice, and getting even numbers on both of them. So let's talk about statistics and parameters. That will help us understand the error term a little bit better. A parameter is a number based on the survey of the entire population. And this can be very costly and time consuming to do, but that's one of the reasons why we only do the decennial census once every 10 years. A statistic is a number based on a survey of just a subset or a sample of the population. And statistics are used to estimate the true percentage or the parameter of the whole population. And if we're calculating a statistic, it's important to know what the margin of error is. The margin of error is usually not reported in a lot of things that we read. But we'll use an example of this with ice cream. Suppose we want to know the most popular ice cream flavor among all BYU students. And we take a survey It will be kind of challenging. I mean, if you wanted to do this for a homework assignment, you got all the email addresses. Imagine how long it would take to follow up with all the students that didn't respond. It would probably take a while. Even for something like ice cream that most of us feel like. So we might do a subset of the whole population, and we can calculate the margin of error, which can help us determine how close we can expect the results to be. The margin of error is calculated by taking 1 over the square root of your sample population. And I graphed this out. On the x-axis, you'll see the sample size. On the y-axis is the percentage of error. And as the sample size increases, the error percent goes down, will decrease. So the larger the sample size, you get a very small error. So suppose we were to sample 100 BYUI students for their favorite flavor of ice cream. 24 students said their favorite flavor is vanilla. 22 of those 100 students said it's chocolate. What's the margin of error?
Oh. Ooh, 0.1.
10%, 0.1. And can we boldly say that vanilla is the favorite flavor of ice cream for all BYUI students?
No,
Well, why not?
because if you add, no, yes, you can, never mind, yes. Because if you add 1 to 22%, it would be, wait, no. No, because then if you do 24 minus 10%, would be the same as 22 plus 10%, right? So then they'd be the same and they overlap.
Yeah, and here's this nice little graph. The chocolate, it is lower at 22 rather than 24, but with the margin of error, there's overlap, and so you don't know, and it could be that 31% of all BYUI students like chocolate, and 15% prefer vanilla, if you look at the entire population. And in that case, vanilla wins over chocolate. And so you can't really say that because the 95% confidence interval for chocolate and vanilla overlap, and so you can't really say that there's a statistically significant difference. Okay, now let's ask 3,000 BYUI students. And 24% said vanilla is their favorite, 22% said it's chocolate. What's the margin of error for 3,000 students?
The margin of error is 1 over the square root of 3,000, right?
Yes.
Wouldn't it be the same as last time?
No, last time we only interviewed 100 students. So the error term was 10%.
The margin of error is 1.8%.
1.8%. Can we boldly say that vanilla is a favorite flavor?
Yes.
Why?
It's a small margin.
It is.
Because the difference is higher than the percentage difference.
Well,
I don't know.
we can't quite say
So
that.
it's still overlap.
Yeah, there's still some overlap. It's a smaller overlap, but because there's overlap, that introduces some doubt, and we can't reject the fact that they might like chocolate more than vanilla. If there was no overlap at all, and then you could make it, you could strongly say that vanilla was favored over the chocolate flavor. But because there is an overlap, there's still some remaining doubt as to which one is preferred. Thomas.
So we were not counting everybody else because everyone else did something different, weirdly, or is it something completely different from each other?
We're not considering yet, I mean, there's, what is that, 46%, so there's other flavors that weren't considered. For this particular survey, we're just comparing vanilla and chocolate. Does this make sense?
Yes.
Is this confusing to anybody? Can we talk about it a little bit more? let's go over some more examples. Let's look at, we're looking at all BYU Idaho campus students, and we can use this class as a sample. What would be our error term for this class? Let's see, how many do we have on Zoom for that? We have 5, and in class we have 4, 9, 14. What would our error term be with a sample of 14? What's that?
I just said very high.
Very high?
So I'm kind of running a blank right now, but like, so we have 14 people in class right now, and we're going to compare that to all of the BYU Idaho students.
Yeah.
Oh.
Before we get the statistic, let's figure out what their error term is.
Is it 26%?
That sounds about right. 26%? So 1 over,
I didn't know how many people are in there.
Well, if it's 26.7, would you want to round up?
27%?
is it 27?
It's 26.7, so for rounding, I'd say 27.
Well, you sound a lot smarter when you bring it out to decimals. 26.7 sounds smarter than 27%. If you read the book, How to Lie with Statistics, that's one of the things we talk about. You'll have a publication that will say, this is,
But they're gonna be sad.
the statistic is 27 point, and then they'll rattle off like 10 different numbers as if anything past the 10 makes that big of a difference.
Doesn't.
So plus or minus 26.7%. So how many students in this class today grew up in a family with 4 or more children? Raise your hand. 1, 2, 3, 4, 5, 6, 7, and then in Zoom land,
You have to have like 3 hands up.
7 out of 14. That's really easy to compute. So 50% plus or minus 26.7%. And so we're looking at somewhere between 76.7% and what is that, 23.3% of all BYUI students grew up in a family with 4 or more children. Is that a good representation of all BYUI students?
No.
That's a really big range. You're looking at, you're uncertain by about half the whole population.
23 then.
Remember the Garfield?
What about, let's do another survey. How many of you are first in your family to go to college, including like your parents' generation, your grandparents' generation? 1.
Hey.
And then how about on Zoom, if you could raise your hand or say something, or text or something, or do a chat? So 1 out of 14.
First, I found
That's
their
Wait, what was that question?
parents.
That's the first in your family to go to college.
I know a person like that.
They're rare.
So what's 1 divided by 14?
It is 7.14, no, 7.1%.
7.14%. More official now. Plus or minus 26. I mean, you can't go below 0.
So 0, wait, it can't be 0.
What would we do in that situation?
So you just say 0,
Okay.
because that's a floor. You're not going to go -0%. So you have somewhere between 0 and, what is that, 33.8% of the BYUI students are the first in their family to go to school. I think the last class there was 1 student, and the one before that, I think there were maybe 3. Not very many. But as you increase the sample size, you can get a stronger precision. Oh, and now we'll do an exercise with M&Ms.
Hey.
Those of you on Zoom, sorry,
Thank you, guys.
I'll pass these out, but if you, before you eat them, if you would please count how many of each color you have.
Dude, this is so fun. Yeah, I'm sure.
Thank you, Mr. Gross.
Thank you.
Don't eat them yet.
Yes.
I'm like,
Wow, you're right.
You know, why don't we do a second, have a few more.
For the last class.
And then all the people on Zoom. For the cookies.
What happens next when we
stupid.
But if you
Man, these
keep
are
track of
exciting.
these separately too.
Oh, so don't combine them?
Yeah.
Everything.
Oh, there's only one yellow one.
Where they go, do you have like a tissue or something?
I didn't get
Blue and
the
orange
orange,
is the
so-
most popular.
I have 3 yellow ones.
I have a mask that you can use to wipe, will that work?
Orange and green are nice.
You're not supposed to combine all the bags. Yeah.
Yeah.
Yeah, you did. Thank you.
Those are the best.
Put these in. Oh, there's good. Yes.
Okay. So
There's
let's
not
do
many
the count.
yellow ones.
Looks like you're making a histogram chart.
Wow.
Samantha, how many, so if you read it to me in this order, it'll make it a little bit quicker. Brown, orange, red, green, yellow, and blue.
Wait, brown, orange, red. Gosh,
It's up on the board.
oh.
Above the screen.
5 brown, red,
5?
yes, 7 orange, 4 red. What's next? 2 green. 12 blue.
Oh, are these for both of you guys?
Yeah.
Okay.
Where we just do one.
So you have, so 37.5% of Samantha's M&Ms were blue. Does that sound like a good representation for all blue M&Ms?
37 and a half?
Yeah, percent.
Look, all my M's are.
It's a lot of ones.
Looks right to me.
Okay, Maggie?
Huh?
How many do you have?
I have 4 browns, I said purple. 4 browns, 11 orange, 1 red, 2 green, 1 yellow, 8 blue. Wait, are we combining the 2 bags? I thought we weren't doing that.
Well, go ahead and combine them, I guess.
Are you shizzing me?
We
Easy.
can do them
there's
separate,
2
either way. Different.
Yeah, let's only put this. Forget that I said that. Are we combining them or no?
Yes,
Yes.
yes or no, either way. Josh, how about you?
It's M&M's and she's.
I have 12 blue minus 1. I'm kidding.
You're
12
you're
blue.
asking me to move my.
Oh,
That's fine, we can do it in whatever order.
okay. 3 yellow. 3 green. 1 red. 3 orange. And 5 brown.
The world we live in.
I have 2 brown, 7 orange, 1 red, 5 green, 3 yellow, and 9 blue.
Oakley,
Okay, I have 4 brown, I have 5 orange, I have 4 red, I have 6 green, I have 1 yellow, and I have 6 blue.
Who's next? Thomas?
Okay. I have 7 blue,
Yeah, you can eat it now.
9 orange,
9 orange,
3 green,
3 green,
1 red,
1 red.
3 browns,
I'm a sweaty mess.
Okay.
and 4 yellow.
And then there's Nikki, you want to go next?
I have 3 brown, 8 orange, 3 red, 6 green, 6 yellow, 4 blue.
I would maybe do that.
Lily?
I have 1 brown, 9 orange, 3 red, 8 green, 4 yellow, and 6 blue.
Kaylee? How many of each do you have?
No,
I just said.
it's my turn.
Oh, did that,
I
okay, Haley.
had 2 brown.
I don't know what.
11 orange. 4 red.
Did you say 4 red?
5 green. 3 yellow. And 8 blue.
I thought you were blind, I'm sorry.
You're good, girl. I didn't even notice.
Alien,
It's supposed to be Haley and hopefully we can use that, isn't it? Or-
I don't.
What's
I'll do an inside joke there. Okay,
Oh. Hey, I fixed my computer so I don't have to use hers for this. I might. She's still having a hard time.
so out of 260 M&Ms, 27.2% were blue. And with your confidence interval, the error term is 6.2%, so somewhere between 21.5 and 33.9 is what you'd expect. But if you look at each one of these observations, so there were 9 of you with M&Ms, and are there any that were, this one's pretty close. Let's see, is that Maggie?
Yeah.
And then this one at 25%, I think that was Nikki or Thomas?
That one's mine.
Okay, Thomas. So both of you were really close to the average, but you see that there is some variance from 13.3% up to 44, almost half. But as we increase the counts, and then you get something a little closer to what the true average would be. Let's go back to our slide. So is 1 bag of M&Ms a good sample? For some of you, for a couple of you, it was really good. Usually it's 2 bags. Does it represent the population well? It might, but I mean, that's the thing with error terms. Even if you have really wide error terms, you might have the exact true population statistic. And your statistic might match up with the whole parameter, but that gets called into question depending on how big or how small what your confidence intervals are. And how many of you like to watch basketball? Okay, well, I shouldn't raise my hand. Okay, I'm glad a few of you do. You know who Carmelo Anthony is? He's a pretty good player.
Better than me.
In 2017, his free throw percentage was 83.3%. And so we could simulate Carmelo Anthony shooting a 1 free throw by tossing a die. The 1 to 5 means he makes a basket, or 6 means he misses the basket. Is this a good way to simulate shooting a basket for Carmelo Anthony or not? Yes or no? No? Why not?
Because there are other variables that could go into it, right?
Yeah,
I'm just thinking.
There's a percentage error.
there's a percentage error.
Yeah.
Yeah, well, if his average is actually 83.3%, 5 out of 6 is 83.3%.
Also, I think he was all alone. I bet he make all 6 of them.
You might make all six, but
He's like other basketball players.
yeah. It would be a good simulation if that were its percentages. And so would this be a good method for other players?
Depending on if they have the same percentage.
Yeah, that's a really good point. If we have the same shooting rate that Carmelo Anthony has, then it would be good, but if it's different, if I were taking shots, it'd probably be every time a six actually makes it, and that's a little more closer to where my shooting average is for free throws. Or when other players have a lot of different levels, so that may or may not work. And we have this exercise where you could throw a dice a bunch of times, but I took, let me pull up this Excel.
I'll show you.
I took this Excel file that I had and I modified it a little bit. So if you were to roll, let me go back to it. So what this is you want to estimate the percentage of times Carmelo Anthony would make 4 free throws in a row. So to do that, we'll roll a die 4 times in a row. And if we roll this, looks like we had a 6 in there. So let's record the shot. And if you do this a bunch of times, a whole bunch of iterations, you'll collect a big data set. And it looks like, let's see, by doing this exercise, let's do it 15 times. We have about 40% of the time he was able to get all four baskets in a row. And 60% of the time he missed at least once. And if you do this mathematically, if you take 5 over 6, you multiply that out 3 times, it comes out to about 58% of the time you would get it. So I mean, with just 15 runs through to 40%, if we were to do this, if we were to sit here and do this exercise 1,000,000 times, I'm sure we'd get a lot closer to 58%. Let's compute a couple of confidence intervals.
Compute?
Yeah. So if you have a calculator or something to do this. US call, so this graph, the chart shows the percentage of US, it's not a chart, it's a graph. It's a chart. The chart shows the percentage of US college graduates thriving in 5 elements of well-being by amount of student loan debt. And so these are, it doesn't say, but these are in terms of percentages. So with no student debt, 49% feel like they have purpose, 47% have a social, but those are different elements of well-being. The margin of error for this study was 1.4%. And is there enough evidence to say that the true percentage of graduates from the 2 different loan populations who are thriving in their community are different from one another? We have 42% and 38%. Are those 2 groups different from each other?
Yeah.
Yeah. Why is that?
One's interested in debt.
Well, so the metric is 42% and 38%. If you wanted to see how close if they overlapped or not, take 42% minus 1.4, and you get 40.6%. 38 plus 1.4 is 39.4. So they don't quite overlap. So you can say that they are different from each other. And let's look at this next one.
They can overlap.
Students with 25 to 50,000 and over 50,000 in their financial, if they're thriving or not, for 26 and 25%, can you say that those 2 numbers are different from each other? Honestly, say no. Why is that?
Because they're overlap and they are very similar to each other because of the error margin.
Yeah, the margin error is causes the overlap. You can't say one's more than the other. And how about these 2 groups?
Yes.
And why is that?
There's no way they would overlap.
No, 5% is really big, and so you're not going to have any overlap. Let's do one that's a little bit harder. This table shows information from a survey of US adults conducted in 2017. It gives a number of adults in the sample without health insurance for 3 different levels of annual income. And is there enough evidence to say that the true percentage of adults without health insurance differs depending on income level? How do we figure this one out? Here, I'm going to write out 3 different groups. One means that people who make less than 36,000. 2 are people who make between 36 and 90 grand. And 3 are the more than 90,000. So what's the proportion of individuals without health insurance in category 1?
3,642.
3642 divided by
21.3.
did I hear 21.2?
21.4.
21.4%. And what's the margin of error? Oh, let me get this check.
It was the one not to be over on would not be on top.
1 divided by the square root of 17,020.
Okay.
It would be 0.98%, I guess. It's 0.76.
6.
There you go. That works.
Well, if it's 6.5, let's just say 0.77%. Does that sound accurate? No?
Yeah.
Okay. And what about the second group? 1785 divided by 18,210?
It is 9.8. 9.8.
9.8%. And then what's our margin of error?
0.74%.
And this last group, 335 divided by 9857?
3.4%.
Okay.
Okay, what's the margin of error? 1%. Based off of these calculations, can we say that the true percentage of adults without health insurance differs depending on income level?
Yes.
Yes, maybe, or for sure?
For sure.
For sure.
Yay.
We can be very confident because 21, these are less than, well, this one's 1%, but these ones, well, these are about 1%. So as the income increases from 36, less than 36 to 36 to 90,000, you see a drop in uninsured from just over 21% to about 10%. And you know there's no overlap, and then it drops again as income level increases. And so I think, so you can say with confidence that there is a trend that the higher the income somebody has, the more likely they will have health insurance. Or the more likely that they won't be uninsured, if you want to use the terms of this chart. Does this make sense? Is this confusing to anybody? You do have a another example.
Wait, quick question.
Yes, Christian.
Okay, I'm just trying to understand how to get the margin of error. The like the 24, this 0.74%, 1%, and I can't read the top one.
0.77%.
How do you calculate that?
Yeah, the error term is 1. How many choose? You can see the screen a little better. Can you see the screen a little better now?
Yeah.
So worried.
As long as I'm talking to this, but it's, so the error term is 1 over the square root of the sample size. So with the first group, we had 17,020. You take 1 over the square root of 17,020, and you have 0.0077 rounded off, which is 0.77%. You multiply that by 100 to get the percent. And then same with the error term, 0.74%. That came from 1 over the square root of 18,000 divided. It's 18,210. So 1 over the square root of n, and that will give you that number with 9,857. 1 over the square root of 9,857 comes out to about 1%, or 1.01%, to be more accurate.
Okay.
Does that make sense?
That's yeah.
And we have one more confidence interval problem to work through. And I think after this one, you should be ready for homework. The following data gives information from surveys of the U.S. adult population in both 2016 and 2017. It gives a number of 18 to 25-year-olds in the sample without health insurance. Is there enough evidence to say the true percentage of 18 to 25-year-olds without health insurance changed between 2016 and 2017? And if you look at this, there's a slightly smaller sample size in 2017, very different in that day. But you'll notice that there are more people with that demographic with health insurance, without health insurance in 2017. Well, let's start working through this. In 2016, what proportion of this demographic were without health insurance?
Fourteen point 14.7%.
And what's the margin of error?
1.8.
What about 2017?
What was the question?
What proportion of this age demographic were without health insurance in 2017? So 522 divided by 3147.
16.5%. I mean, 16.6%.
What's the error term?
It is
0.17, 0.8, right?
1.7.
1.8%?
Yeah.
About
Can you say that these two numbers are different from each other?
yes.
Yes, why is that?
Because they aren't overlapping from each other.
Well, let's see. What's 14.7 plus 1.8?
Oh,
16.5? What's 16.6 minus 1.8?
14.8.
So they do overlap. So you can't really say, because of that overlap, you can't say that those two numbers are different from each other. Does that make sense?
Yes.
So I have a question.
Yes.
So when you say they're not different from each other, that means like basically the data that they gathered is basically saying the same thing.
Yeah.
Okay.
I mean,
They had a bigger sample size, then they
Yeah.
did more.
Percent.
maybe, but if you have a bigger sample size, you may end up coming to the same conclusion that the number of uninsured people of the demographic, 18 to 25-year-olds, has not changed. You might come to the same conclusion, but you might not. But I mean, as close as it is, it's likely you may not. I guess. I mean, I don't know. We can speculate all we want, but it's when if you're reading an article that talks about changes in insured 18 to 25-year-olds from one year to the next, you can't really. If they're claiming that it's gone up because it was 14.7%. Now we're at 16.6%. Therefore, there's an increase of almost 2%. You can't really make that claim because of your age. It may have actually gone down a little bit. It's not significantly different. Are there any questions about this? This probably work here.
No.